All right, so while you guys are getting settled down, let me go ahead and do a very quick review of the real work, real energy method that we had talked about last time. I basically told you that the way this real work, real energy principle works is for any structure that behaves in a linear elastic manner. If, for example, this is a column, a linear elastic structure, I apply a load P to it slowly uh, so that it deflects very slowly to its final deformed configuration with a displacement of delta. Then the external work done by me, by the external force, in going through a displacement of delta is how much? Half P delta, not P delta, right? Because we are applying the load slowly, we are not applying the entire force free at once. So external work done, real external work done is always half P times delta. And during that deformation, the structure, if it's a beam type structure, it is going to bend and it's going to store energy within itself just like a spring would. If it's a truss type structure, then each and every member of the truss would either contract or expand and store energy within itself. And I pointed out last time that truss members really essentially are straight members which can either have compression or tension. So essentially they behave like springs themselves. So we went through this couple of examples of how you can find unknown displacements. So for example, a cantilever beam with a tip load, if I'm trying to find this unknown displacement, I can do external work done by this force P, half P times delta. We can calculate the internal energy stored in the beam in the deformed shape, in this deformed blue shape, by calculating the bending moment diagram and integrating integrating half times m over ei over the entire length of the beam, and that's how we found internal energy stored. And if you equate external work done to internal energy stored, we can find that one unknown delta, uh, which we obviously got the same answer as we got with all the other methods. Another example I gave you was this one, simply supported beam with M. Again, the external work was half m theta. Internal energy stored was obtained by the bending moment diagram, half times m square over ei integral. Equate those two, and we get again the unknown rotation at the end. One thing I'll point out here is that to apply the principle of real work and real energy to find some unknown displacement, you can only find one unknown, because the overall equation that you have, WE is equal to UI, there's only one equation. And you can find only one unknown with that. And that unknown also is very specific. For example, if I have this cantilever column and I apply a load P here, then I can only find the displacement under this load. The displacement, this half P delta, that delta is the only unknown displacement I can find. Similarly, for this applied rotation or applied moment, the amount of rotation at the point of application is the only thing I can find. That's a big limitation, of course, of the principle of real work and real energy, but we'll see how we can get over that limitation as well. So last time, our TA, Hoy, was introducing this example to you, but we didn't quite get through it. So we'll take, and I think we discussed a little bit of how you would approach this. We said that there's this simply supported beam with two overhangs. There is a load P applied here, load P applied here. And what we want to find is the displacement delta either at A or at D. Now, this might seem a little conflicting with what I just told you. I told you that real work, real energy principle works only when you have a single force and you want to find the displacement under that single force or moment. But here, clearly, I have two forces. But the good thing is that the entire structure is symmetric. Those two displacements are also equal. So we can find those two displacements, as I'll just show you. And I think we talked about how you can draw this approximate deflected shape. We can calculate the shear force and bending moment diagrams as well. So first thing, you should be able to see clearly that the reactions at the 2 points would be P and P. No surprises there. Um, you can draw the shear force diagram by just following the applied loads. So P down and constant minus P all the way till here, jump up by P, 0 in the middle section, jump up again by P, constant P, and jump back down to 0. That's the shear force diagram that we have for this beam. The bending moment diagram, would it be positive or negative? Positive bending moment or negative bending moment? Negative. It's a reverse curvature throughout the length. So indeed it will be negative starting from 0 at the tip, and it will go straight line negative. What's the value here? Minus P times A. That would be remain constant here because shear force in this middle section is 0, so no change in moment. And then increasing back up to 0 moment at the tip. That's the bending moment diagram. So using the real work, real energy principle, what is the external work done on the system by those two forces? So I have this beam, and those two forces at the ends are doing work on it. And as they do work, the beam bends down and it undergoes certain displacement delta. So what is the work done by one of those forces? Right. One of the forces will do half times P times delta, just like any other external force would. And the other one would also do exactly the same amount of work. So I'll write it as such: half times P times delta plus half times P times delta gives me P times delta. And the internal energy stored, we would have to calculate how. How can I calculate the internal energy stored after the application of those two forces when the beam bends? Say that again? Yes, we'll integrate, but what should I integrate? Okay, half m square over EI, which we get basically by saying half times m as a function of x. This is the bending moment, m as a function of x, multiplied by the curvature, which is another m as a function of x over EI. Right? Half times moment times curvature is the internal energy stored within a section of the beam. This is an argument that we went through about in detail last time. And if I integrate that over the entire length of the beam, then that would give me the total energy stored in the structure. So I won't go through the algebra of this, but maybe I'll write the equation here. This integral can be broken up, and actually instead of calling it L, I'll call it 3a. So this can be broken up into an integral from 0 to a of half times, what is the equation of the moment here? Okay, so minus P times x square over EI dx. I'll write another integral plus integral from a to 2a. The moment here is constant, so half times minus PA square over EI dx. And what about the third segment? What would be the energy stored in the third segment? Same as the first one. It's a symmetric structure, right? So I can just take the first one and multiply that by 2. And that would be the total energy stored in the structure. Make sense? And I won't go through the details of, well, maybe we can. It's not too bad. So minus will get squared out. So we'll have from the first one, P square over EI, half and 2 cancel off. X square becomes a cube over 3, and plus half times P square over EI, well actually A square as well, and another A. So this turns out to be 5 over 6 P square over EI A cube. And if you equate the external work to the internal energy, then we immediately see that delta is equal to 5 over 6 P over EI A cube. Make sense? Any question about this one before I jump into the next one? And the next one we'll do as a in-class exercise, which you can do in these groups of 4 or 3 or 4. And then at the end of the class, I'll collect them. Any questions on this one first? So maybe very quickly, I'll reiterate what I did here. Of course, for this structure, the first thing to do, for any structure, the first thing to do is to draw the internal forces, in this case, the shear force and the bending moment diagram. The next step is to calculate the external work done, and then the internal energy stored in this entire beam in this deflected shape, and then equate those two and find the unknown displacement. Pretty straightforward procedure. Okay. All right, so let's try this next one. So you can take a minute, try to attempt it by yourself first, and then I'll give you some more time to talk to your other members of the group. Make sure you are all on the same page, and then we'll do it together in class. So maybe I'll state the problem here as well. This is, again, the same structure, exactly the same structure, but the loading is different. I have a moment, external moment M applied at B, external moment M applied at C. And I'm asking you for the displacement at A and D. And once again, this is a little bit of a contradiction to what I just told you, that for real work, real energy, you can find the displacement at the point of the application of the force or moment. But here I'm asking you to find the displacement, and I'm applying a moment. But once again, you might be able to take advantage of symmetry or anti-symmetry or something. And let's see if that hint gives you some ideas. So try it for a couple of minutes first, and then you can work in groups. All right, everyone. So let's bring it back. Any ideas on how we can proceed with this? Of course, I know you won't be able to finish it within this 3-4 minute period, but any ideas on how we can go about doing it? Go ahead, Naso.
Find the deflection at either B or C, and then
find the deflection at B or C. You mean rotation?
Okay. Sorry, the rotation, and then since there's no moment, it's not going to be bent, and then use that angle multiplied by angle.
All right. Yeah, I think that's the right approach. So what Nafal was saying was that we have these two moments here. Clearly, the structure is symmetric, but the loading is anti-symmetric, which means that the response of the structure would be what? Symmetric or anti-symmetric? Anti-symmetric. And we can see that by actually drawing a rough deflected shape here. So let's see if I can do that. I'll draw the section in the middle first. Let's think about only the simply supported beam part between B and C first. If I had a simply supported beam with two moments acting on that beam like this, what we would likely see is something like that. Does that make sense? Mm-hmm. What about the two ends? The two ends out, they remain straight. Why is that? There's no movement here. There won't be any curvature. So indeed, those two sections will just remain perfectly straight and anti-symmetric, where the line of anti-symmetry is right here at the center of the beam. Now what the problem is asking you is for this displacement, either displacement at A, and as you can see from anti-symmetry, it would be exactly the same displacement in the opposite direction at D. So how can I find that displacement? Mubin? Go ahead. Okay, so yes, one way indeed is to find the rotation at this point, or equivalently the rotation at this point. So that would be theta, and it would be exactly the same theta here. So if I know theta, then I can take this length A times theta would be that delta, right? I'll write that delta is equal to theta times A. So essentially, we have boiled down the problem of finding delta to the problem of finding theta. Now for theta, I can indeed apply the real work, real energy principle, because it's only one unknown. Theta is the same unknown at both those locations, and the amount of the moment applied is also the same. So if we apply real work, real energy, then we can show that external work done by the application of those two moments, what would that be? The total would indeed be m times theta, but this m would do half times m times this theta, and of course this one would do half times m times this theta. So we have a total work done m theta. And how can I calculate the internal energy stored? Yeah, I need to have the bending moment diagram and consequently the curvature diagram. So for that, I'll need to find reactions and do the shear force and the bending moment diagrams. What are the reactions for this? 2m over A, what is that? Total equilibrium of moments, it will be the total moment on the structure is 2m. So reactions would be, I hope my pen hasn't stopped working. Uh-oh. Let's see. Okay, great. So yes, the reactions would be this one pointing down 2m over A, and this one pointing up 2m over A. Hope everybody sees that, the reason for that. And clearly the shear force would then be just 0 all the way here, go down, and is that right? Oh, so the total moment is going this way, this additional moment, yes. Thank you. Let me delete that. Indeed, yes. Thank you. And let's see. So we'll go up by 2m over A, and then constant and down, and then constant 0 here. The bending moment diagram would of course also be 0 all the way here, and then what? Goes down to a value of minus m. Why is that? Because at this point, the curvature has started to be negative, right? And if you were to take a section here, you would see that the bending moment at that section is indeed minus m. So we would go down to minus m, and then what? Linearly back up to positive m, and goes back down to 0. So this would be minus m, this would be plus m, and this is 2m over A. That's my bending moment diagram. And what would be, well, the curvature diagram would just simply be a bending moment over EI. But what would be the internal energy? Anyone? How do I calculate internal energy if I have the bending moment diagram? It's That's right. So it's always half times mx times m over EI, also as a function of x, half times bending moment times curvature, and integrate that over the entire length of the structure. In this case, I don't need to integrate outside of A and 2A, so I'll just set the limits A to 2A. And this equation, I believe if you calculate it, will turn out to be minus 3m plus 2m x. You can check that. If I plug in x equal to a, I get minus m. If I plug in x equals 2a, then I get plus m, right? So that indeed is the equation for the bending moment within that section, and we can use that. So integral from a to 2a, half of minus 3m plus 2m x whole square divided by EI dx. April? Say that again. The second term, this term? Yes, thank you. Yep. Because of course, otherwise it would be dimensionally incorrect. So if we do that, and I'll make that correction here as well. 1 over 2 EI x over a, and the whole thing is squared. I won't go into expanding it, and I'm sure you can do this integration. I'll just write out the final value that you should get. What you should be able to find is that it's m square a over 6 EI, and that clearly implies that if I equate external work done to internal energy stored, then theta would be equal to ma over 6 EI, which implies that delta would be equal to ma square over 6 EI. Okay. So once again, what we did in this problem was to first make sure that that the unknown that was asked for, the delta at A and D, we express that in terms of the unknown that we can actually calculate using real work and real energy. We converted delta to theta, and then found theta using the simple principle of external work done is equal to internal energy stored. Always external work, real external work done will have this factor of half times m times theta, or half times p times delta. And this is extremely important because in a very short while, actually right now, we're going to start talking about a different method, a method of virtual work where this half is not included. So you have to be really sure about what we are talking about, whether that half should be there or should not be there. Okay, and I'll go through that conceptually again. But before I do that, any particular questions about any one of these steps for this problem, for either of those two examples? All right, so we'll continue on, but please do keep that paper separate, and at the end of the class, make sure you turn it in to me, even if I forget to ask for it. But let's now try to move on to something else. As I mentioned, the main drawback of the real work, real energy principle is that you can find exactly one unknown. In these two problems that I showed you, it was either that delta under the load or theta under the moment. But if you want to find something else, so for example, on the previous page, um, on the previous example here, if I asked you to find the rotation at this end, rotation at the free end, you cannot find that using the method of real work and real energy. You would have to resort to some other method. But what we are going to do now is to try to take advantage again of principles of work and energy to try to calculate something just like that. Um, we we will look at this example that we have seen before as well, and let me see if I can pull this up somewhere here. Right. Maybe last lecture or the lecture before, I had introduced this particular example. You had done this example for your homework one using, I don't know whether you used the geometric methods or some people actually used virtual work method. But last time I showed you that you can find this delta x again using the method of real work and real energy, because external work done would be half times p times delta x, and delta y, it would not contribute to the work done. And the internal energy stored would be simply a function of the internal forces in these two members. So we found that we got the exact same answer as we got for homework one using a different approach. But now the question is, what if I want to find delta y? Delta x we can find with real work and real energy, but what about delta y? How can I find delta y? Okay, and that's the problem that we are going to try to solve. So for that, we'll do a little bit of a thought experiment first. And this goes back to the concept of work done in the presence of another force that I had talked about. So maybe I'll talk about this a little bit first. If I have any structure, a free structure, there's no load on it. Okay. Now I apply a small load P prime, and it undergoes some deflection. There is clearly some deflection from here to here. And if I were to plot the external force, you can see that it goes up to P prime, and it also has some small deflection delta. But now the second stage of the problem is the more interesting part. What we are saying here is that keeping P prime in its place, I'm not going to change P prime. But on top of P prime, I'm also going to apply another external load P, the actual real external load P. And when I do that, this structure is going to have an additional displacement of delta. So last time I believe we had gone through this logic of what would be the external work done by P when it goes through delta. That would still be the same green triangle that we've been talking about. It would be half times P times delta. The external work done by the additional force P is still the same. But there is some additional external work done by this force P prime as it goes through the displacement delta. Why does P prime do work even though P prime itself is not changing? P prime is the load that's been applied there and stays there, but it's not changing. So when an additional load P is applied, why does P prime do any work? That's right. So P prime has been applied there, and when the other, in addition to P prime, when the other external load is applied, P prime also moves, right? So force times distance is the work done. And clearly when P prime moves through this amount delta without P prime being changing, that amount of work is this rectangular, yellow rectangular area. So this is the concept that we'll rely on in doing this thought experiment. What we'll do is, since we want the vertical displacement delta y, we'll apply some small unknown virtual force P prime, okay, to this structure. Some very small virtual force P prime that we don't care what the P prime is. All we care about is how much work does this P prime do when the actual load is applied. So the logic behind this principle of virtual work, or the method of virtual work, is that given any structure, if I want the vertical displacement at C, I'll go in and apply a vertical P prime virtual load at C. And then in the presence of that vertical P prime, I'm going to apply the actual real load P on top. Okay, so what will happen? P prime will move through a distance of delta y. P prime will remain constant through that movement delta y. That would be the external work done by P prime times delta y, and that would also be equal to the internal energy stored in this structure as uh, as this structure deforms from point C to this new point. And we'll talk a little bit more about this, how it goes about. So overall, what we are doing, first apply a virtual load P at C at point C. When I do that, the structure will deflect a little bit. I'm not even going to show that deflection. It's a very small load that that we don't really even care about how much is the deflection for. So, but I'm just showing you here that the structure will deflect a little bit. This first plot, what I'm plotting is external load in the vertical direction, and consequently both of these members will have internal forces within them. If I apply a P prime here, you can actually resolve that along the directions of these two members, and you'll see that this member would be 4/5 compression, this member would be 3/5 P prime, also compression. Now in the second stage, what we are doing is we are applying the real force P very slowly. So what would happen? If I plot the displacement of P prime, it has already reached the value of P prime and small delta prime, which we don't care about from the first stage. And the additional work done would be this constant P prime times the unknown delta y that I'm trying to find. So that's the most important concept to make sure you understand here. This plot right here is showing you that from this point all the way to this point is what the external work done is the contribution of the external to the external work done by P prime, if that makes sense. And this plot shows that up until this point there was no real P, there was no real horizontal force, and then we slowly applied this actual real load. The work done by the actual real load is still a green triangle. The virtual work done would be this yellow rectangle. And since the total external work done would still be equal to the total internal energy stored, this yellow rectangle would be equal to the energy stored within these two members due to these two forces. So what we are saying really is that had I not applied this virtual force at all, okay, if I had not applied this virtual force, if I had just applied the real force, then the real force would have done some work and it would have stored energy within those two members. The real work done would be this green triangle, and the internal energy stored within those two members would be these two smaller green triangles. Since this green triangle, the area of this green triangle would be equal to the sum of the areas of these two green triangles, because this is the external work done and internal energy stored in the first case. Therefore, in the second case, when I do apply this P prime, the yellow rectangular areas must also be equal. Is that logic making sense? All right, let me try again. So we have, let's go about it this way. So I have some green triangular area. That's the external work done. And I'm saying that all of that external work done gets stored as internal energy within the two members of the truss. Okay, so if I were to not apply the P prime, the virtual load, if I did not apply the virtual load, I should be able to say that yes, this green area of the external work done is indeed equal to these two, the sum of these two green areas of the internal energy stored. Okay, so that's part one of the argument. That is part one of the argument. Now I'm saying that in a second case, in a different case, I have this virtual P prime applied. So I'll start with my yellow rectangular area, and on top of that there is this green, exactly the same green area when I apply the real load. Okay, when I apply this real load, all of that energy does get stored into the same two members, but now because of the work done by P prime, those two members will also store some small amount of energy due to P prime. So the work done and the internal energy stored would still be the same under the, even if I apply P prime there. So what the argument really is that if I want to show that the virtual work done, which is the yellow rectangular area, if that virtual work done is equal to the virtual internal energy stored, so this yellow rectangular area is the sum of the internal energy stored, then the way to show that is by saying indeed that this total area is the same as these two total areas. Since the green part of the area, we have already shown this part is equal to the sum of these two, therefore yellow must also be equal. Okay. All right, so think about it if it doesn't make sense, and we'll talk about this more next time. But let me proceed with how you can use this. Strangely, this seems to have already been completed. Oh, did I? Yep. Okay. So in this case, the external, is it complete in your handouts as well?
Yes.
Okay. But anyway, so I printed off the wrong PDF, but let me just reiterate again. External virtual work done by P prime when it goes through the displacement due to the real P. So when I apply real P, that would be, so as I apply my real force slowly, and as it goes through that displacement here, the internal force in those two truss members would be what? 3/5P tension and minus 4/5P, that's compression, in the presence of whatever internal force was already there due to this P prime. So the external work done by P prime would simply be equal to, and I'm going to write that as a virtual. So everything virtual has this dash, has this prime on top. Now,
Should that be delta x and the green triangle?
which one?
Or not?
This guy?
Yeah.
You're right. This should be delta x, because the real work done is indeed in the delta x direction. Thank you. So the work done by this P prime as it goes through this vertical displacement delta y is P prime times delta y, not half P prime times delta y. Why not half? I've been just telling you that real work done by a force is half P times delta. But the virtual work done by a force that's already existing, it has already reached its full value of P prime, and then it goes through a displacement of delta. That's why the virtual displacement or the virtual work done is P prime times delta. That's the yellow rectangle. Okay. And this is an extremely important point for you to understand when to use that half and when not to use that half if you understand this thought experiment. Okay. So we'll go through this again and again quite a few times over the next few lectures. So, but you think about it, come up with questions, post them to the discussion forum or bring them to class or to my office hours, which reminds me, since Dr. Liu is not here today, she will not be holding office hours this afternoon. Instead, I will hold office hours. You can come by my office. Miles?
I just want to make sure of this example, which one's the real load that's applied? Is it P prime?
Yes, in the example, this example is the same example as your homework. This was the original structure, and the horizontal load is the real load. Anything with a prime is virtual. Okay. So the external work done is P prime times delta Y. The total internal energy stored would be NAB prime times real NAB L over AE plus N, I think it's AB, right? And BC. No, not sorry, not AB, but AC. Let me write that again. NAC prime times, so that this is the virtual force within the member times the real displacement, which would be NAC times L over AE plus NBC prime times NBC L over AE. And without going through the details of the calculation, we can show that if I equate, sorry, I should write that this internal energy is also UI prime. So with the real work, real energy method, we were equating WE to UI. Those are both real work and real energy. In this principle of virtual work, we are computing the virtual work done and we're equating it to the virtual energy stored within the system. Okay. And in this case, I'll just write the numbers here. For NAC prime, this is minus 4 over 5 P prime, minus 4 over 5 P prime, times real NAC, which is 3 over 5 P, so 3 over 5 P times L, which I believe is 3 meters. Or maybe I'll just write it as LAC plus minus 3 over 5 times P prime times minus 4 over 5 times P times L BC. And if you compute that out, you can cancel off this P prime, external work, with this P prime and this P prime. So that's the another reason why P prime does not matter. It does not matter what is the amount of P prime you apply, as long as it is very small and as long as it does not affect large deformations. Okay. So anyway, we'll stop here and we'll continue with this logic again on Wednesday. Keep in mind, homework 2, part 2 is due tonight, well, at 5 p.m. This Friday, we will have our first quiz in class, and I'll post a sample quiz right after the lecture. You can take a look at that sample quiz. Make sure you try it as a sample quiz. See if you can finish it off in 40, 50 minutes. And of course, I'll be available for questions. And as you're walking out, yes, please do turn in your sheet of the in-class assignment, and I'll see you all on Wednesday. Yes, all of you have to turn in that one sheet. Go ahead.
So the piece is doing everything but work virtual work, right?
Not virtual work, only real work.